So that's kind of, I mean, it'll be a nice byproduct because when it comes time to take the Unit 3 test, you'll still have a couple of differentiation topics, so derivative topics on that assessment. Right. So anyway, Rolle's theorem says if f is a continuous and differentiable function on the closed interval a to b. Right. So just flash back like a month and a half, 2 months ago. This is something that may not have made any sense, this statement, but now we've discussed continuity in our limits unit. We've discussed differentiability when we talk about finding the derivative and knowing that that derivative exists at all relevant points on a closed interval a to b. And if f of a and f of b are equal, then there is a location c on the interval where the first derivative is equal to 0. All right. So this one, it's kind of an interesting topic because if this were an in-person class, I would demonstrate this using an old school technique. And that old school technique would just involve a piece of string, and that would be it. I mean, I could try to do the same thing here, but then you got to look in the camera and it's kind of a pain. And also, I don't have any string. It's weird. I have everything that you could possibly want in a classroom, but not at home. No, I got a wire. I can make it work. So what's happening is you have f of b equals f of a. You know, by the way, I'm just going to double check. Yes, I am recording. Good. All right. You have f of b is equal to f of a. So we'll start with that. So I'm going to create a quick sketch here. I have a, I have b, I have f of a and f of b. And we're saying f of a and f of b are the same thing along this function, right? So it's indicating here that there's a point in space, a comma f of a, that has the same height as b comma f of b. Height as in distance away from the x-axis. All right. So whatever this height is, it's the same for both. Quick sidebar. Today in my algebra classes, I'm teaching them, it's the very first day where I'm teaching them function notation, like what f of x means. And I don't think I'm wrong when I say that moving forward, if they don't have a good sense of what function notation represents, f of x, g of x, things like that. And even this actually is leftovers from something I was working on in extra help in my high school class today. If they don't have a good idea of what function notation represents, then they would have no hope of understanding what this notation is talking about, right? I mean, it makes perfect sense, you would think, right? But anyway, so the heights are the same. We don't know what it is, but we know that they're the same, all right? So what this is telling us is that the first derivative, and again, first derivative is a measure of slope, right? Instantaneous rate of change or slope at a point, right? That's going to be equal to 0. If the first derivative is equal to 0, then we're looking at a horizontal tangent. All right. So a couple of ways that this could play out. It could be that there's just a singular line segment connecting these 2 points. That's possible. In which case, the derivative at any point along the interval, the closed interval from a to b, the derivative would be equal to 0 because this would be a constant relation, constant function as it turns out. All right. So that's one possibility. Another possibility is that it's some kind of curved function. Right. But if it's guaranteed that the 2 endpoints have the same height, then there must be, if let's say, for example, it starts off going in the upward direction, it still has to come back down and grab this point. So in order to do that, there would necessarily, assuming it's continuous and differentiable, there would have to be some kind of turnaround point or turning point or vertex along this domain. That would be another instance where it would play out. I don't really want to highlight. Oh, I'll just sketch it. All right, it could also go the other way. All right, so maybe it goes downward. So my little my string example is basically saying that I have a piece of string, or I'm using a wire here, and wire, you know, it's a little trickier with a wire. But if I tell you that the two endpoints are at the same height, right? They're at the same height. It could play out that it's horizontal. It's a horizontal line segment, in which case the slope is 0 all the way through. Or it could play out that it bows downward, as in something that's concave up. Or it could go the other way. Actually, I think a wire is probably better than a piece of string because I can actually get it to go in the upward direction. But by having these 2 points at the same location, it forces there to be a turning point. Now, if the 2 points are at different locations, the 2 endpoints are at different locations, it's not guaranteed that there'd be a turning point along the domain. All right, it could be concave down like you see here, but there's no guarantee that there would be actually a turning point before it gets to the endpoint. Right, same deal on if we change the orientation or change the concavity, things like that. If the heights aren't the same at A and B, then everything falls apart. But if the heights are the same, then it all works out. Right, so you could have something really crazy. I'll just duplicate this. My hesitation there was I was looking for a duplicate function for some reason. Like, how many times do I have to use this app before I can realize how it works? All right, so you could have something really crazy. Something like that. All right. Then there is a location C on the interval where the first derivative is equal to 0. Right. Still holding on to that relationship. Let me just move this over. The conclusion is still valid, even though there is actually more than one location. It still follows the same rule. Right. So we're still good to go with that statement. I'm actually going to move this, I guess, and smidge these down a little bit. All right, but then so these satisfy Rolle's theorem. These are perfectly fine, right? But and I already gave you an example of how it wouldn't work if the 2 endpoints were at different heights. But let me give you an example where you could have the endpoints at different heights, yet it still may not work, right? All right, this is a case where it's not a continuous differentiable function entirely over the interval. All right, so this is an instance where Rolle's theorem fails. All right, so the first 2 are fine. We have instances where there would be a horizontal tangent, instances where the derivative has a value of 0. All right, so Rolle's theorem checks out. I have a horizontal tangent here. I have one up here. All right, I can actually make the second one a little teensy tiny one. All right, these are 2 separate graphs. I graphed them both simultaneously, but they're 2 separate graphs. That's why I color coded it. All right, so each one has its own turning point. This one is a single function that has 4 turning points. So this one's legit by Rolle's theorem. But the last one doesn't check out. All right. So Rolle's theorem checks out. For the first two. That's a poor quality error. All right, but the last one is the instance in which it fails. All right. So just a few sketches. If the heights aren't the same, we don't even think about Rolle's theorem. It's when the heights are the same, that's when we get into that conversation. Making it look a little bit nicer. All right. So that's Rolle's theorem. And we'll get into examples in a minute. But then we have the mean value theorem, which is a little bit, actually, I was going to say a little bit more relatable. It's actually a whole lot more relatable, right? What this says is that on the closed interval A to B, there's a location C on the interval where the instantaneous rate of change, also known as the derivative, is the same as the average rate of change, right? And so what this is, and we'll do some sketches here also, but intuitively, it's basically the same as, you know, like, or you're driving to work, driving to school, whatever, and so you want to figure out how fast you're going on this trip, right? One way that you could do that is to take the distance that you've traveled. You know, it's I got like, I think it's like a 25-mile commute every morning, but it takes me roughly 45 minutes to get there. So I would take 25 and divide it by 0.75, you know, because 3/4 of an hour. Divided by 3. So really, it's only like an average of 33 miles an hour. Okay, well, whatever. It's not fast because I'm a lot of back roads along the way. But anyway, you get your average velocity, which is telling you on average how fast you'd be going. However, you know you weren't going that speed the entire length of the trip because you know you came to a stop at a red light a couple of times. You know that you took a little stretch on the highway where you're able to go 65 miles an hour, but then you got stuck behind a school bus, which was going 20 miles an hour, right? So there's fluctuations in your trip in terms of the velocity. But you do know that at some point in your trip, you had to have gone, I believe it was 33 miles per hour that I computed just now, all right? So at some point in your trip, you traveled whatever that average rate of change was, right? So visually, it's pretty easy to identify because, especially with this app, it's pretty nice. Let's say you have a closed interval on A to B and some arbitrary function. I'll make it funky, but not too funky. You know, my typical arbitrary function. All right. So here's f of a, or a comma f of a. So the first step is kind of like the same as Rolle's theorem, which is why they're grouped together conceptually, but also they're easy to confuse with one another. Honestly, I gotta say that most of the time when people mess this up, they mess it up because they get the mean value theorem confused with the other theorem. I'm just gonna make this graph look a little nicer because it looks a little shaky because of my shaky handwriting. Okay, okay, not even giving me, no. Come on, I want to get a little bit of, I can't even get to it. All right, I'm just gonna move this point up a little bit. So anyway, that's gonna be b comma f of b. The average rate of change would be the slope of the secant line connecting point A and point B, or a comma f of a and b comma f of b. So I could take this line. All right, that red line is the average rate of change. All right, the average rate of change, also known as the slope of the secant line. All right. Now, good, useful piece of information. On average, what's the rate of change? You know, that's not bad information to have. I'm going to make this a little thicker. wrong thing got deleted. There we go. All right. What the mean value theorem, and by the way, mean value theorem, average rate of change, that's a pretty decent mnemonic, because mean, thinking in terms of statistics, mean and average mean the same thing. So average rate of change, mean value theorem, that usually gets the job done for folks. All right, I'm going to shrink these down because I need a little wiggle room here. All right, so, oop, that moved on me. So what the mean value theorem is saying is that at some point, this function is going to have an instantaneous rate of change that's exactly the same as its average rate of change, assuming it's a continuous differentiable function on the closed interval a to b, right? Which just basically means it's a smooth curve over that interval, right? So what I can do to illustrate that is take a line with the same slope and just trace it along the curve until I can show that it has, as a tangent, the same slope as the average rate of change. This is going to get overshot, so I'm just going to move it. It's like I have no good place to put this a comma f of a. But if and there's actually another place I could put it over here, but that's a little even a little messier. But I got a location right here where the tangent line slope is the same as the secant line slope. All right, you can see they're parallel to one another. All right, so this is the instantaneous rate of change. All right, so that is a demonstration or an illustration of the mean value theorem. I mean, I could try to get it in here. Let me just move some letters around and stuff. And just kind of put it there. It looks a little crowded, but you can kind of see at this location here, there would be another instance in which the average rate of change and the instantaneous rate of change would be the same. I can actually trim this down a little bit and just kind of throw it in there. Might look a little bit better. All right. And I can do the same thing with this one. Because each of these represent tangents, throw little arrowheads on them and make them stand out a little bit more. Actually, here's a novel idea. Let me just change the color. You can tell when it's a long week when you just can't come to like things that normally come easy to you take a little longer, like processing mentally. Like the idea of changing colors should have came to me like 5 minutes ago. It didn't. I have no excuse. And so here's an instantaneous rate of change. I gotta say, this diagram is going to look glorious when I'm done, but just a question of will it ever be done? All right. And so here's my average rate of change. And finally, I got to figure out how to get my f of a in there. And nice and tiny. There we go. It looks glorious. So those are two instances where the instantaneous rate of change and the average rate of change are the same. All right. Now, conceptually, we have the driving to work analogy. Graphically, we have this, but now we need some sort of practical application of it. And, practical application as in like a problem or two where this plays out. But we also would like to have some real practical applications of it where we can sort of dive into, a word problem or two that applies this content. All right. So find the values of x that satisfy the mean value theorem, MVT for mean value theorem, for each of the following. Now, FYI, this is I'll call it a typo. Should be parentheses around the S because it could be more than one, but we don't know that there's going to be multiple. So if somebody's in need of typo bonus for unit 3, perhaps you can get on that. So anyway, what we would do, again, over this closed interval is determine the average rate of change. We have an A value, we have a B value. The average rate of change would be determined by y equals f of x. Okay, this is a function of x squared is a quadratic function, so we're good to go there. So f of b minus f of a over b minus a. That's shaping up nicely. Hold on, angle my arm here a little bit. All right, so f of 5 minus f of 1 over 5 minus 1. All right, now how you come up with f of 5 and f of 1 is up to you. I don't know that we need Desmos for this because plugging a 5 into x squared shouldn't be that difficult, but you know, sometimes at least the safety net is worthwhile. All right, so 25 minus 1 over 4, that's going to give me a 6. That's the average rate of change. All right, average rate of change or slope of the secant line. It's a pretty common abbreviation, AROC. You see that a lot. And I didn't come up with it. It sounds like, you know, somebody trying to make math seem tough, you know, tough and cool. But it's just an abbreviation. You know, it helps, right? As opposed to the IROC, instantaneous rate of change, which, you know, IROC is something else too, but something actually cool, or at least in the 80s it was. So we need f prime of x, which would be 2x, right? Just simple power rule. Now, what the mean value theorem is telling us is that there will be some value of x, assuming that this is a continuous differentiable function, and when you're dealing with a quadratic, you're dealing with continuous differentiable functions for all values of x. There will be some instance in which this is equal to this. All right, so that would be the instance where 2x is equal to 6, meaning x is equal to 3. All right, so that would be the value c over the interval. All right, now c as in some constant value or some other value over the interval from a to b, but we just solved for x. So you know what they'll do is they'll say, all right, so we need to evaluate, and I'll show you the quote unquote proper way of doing this, but I feel like it adds an extra step that's sort of unnecessary. So what they're saying is that there is some constant value c that if you were to evaluate your function f prime at that constant value of c, you'd get 2c, right? So then what they're saying is take that 2c and set it equal to 6 and solve for c. But if you know that x is equal to c, under this circumstance, you can skip that step. But this is technically the by the book way of doing it. Either way, as long as you come up with 3, it's fine, right? So it's just weird, you know. Whenever you designate a value, it's kind of like when we were doing linearization, where it's like at x equals 2, but it's really at x equals a, so therefore a equals 2, but doesn't that mean x equals 2? You know, well, only in the instance when x is equal to 2, because x is a variable expression, a is some particular value that X can take on over its domain. You know, so it's just, I mean, it boils down to semantics. You look at it and say, all right, now we're just getting technical about it, you know. At some point that'll matter, but at this point it's just a matter of just going through the process. Either way, bottom line is the number is 3. So whichever way you want to go on this is fine by me. All right. Now for number 2, f of x is equal to sine of x. All right. So same idea. We need to find the average rate of change over this interval. So it's the same structure, f of b minus f of a over b minus a. Right, so we know that f of b, I'm just kind of for the sake of space here, we know f of b would really be f of pi minus f of 0. So, oops, ab over pi minus 0. Sine of pi is equal to 0. Sine of 0 is equal to 0. Pi minus 0 is equal to pi. So we get a result of 0. Right. So what that tells me is actually, this is sort of like the, it's sort of like a combo deal, because what we just got is a situation that will actually satisfy both the mean value theorem and Rolle's theorem, right? Because if I evaluate my sine function for 0 and pi, I'm going to get the same y value, 0 in both cases. And I just showed that the slope over that interval is equal to 0. So now what I'm looking to do is show that my derivative is equal to 0 at some c value along that interval of a to b, which is implying Rolle's theorem indirectly, because like one leads to the other anyway. That's a cool consequence. So f prime of x is equal to cosine of x. So I would want to say, if I'm using this approach, I guess, just to settle on one thing, I would say there is some value c that would allow my cosine function to have a value or take on a value of 0. So cosine of c equals 0, and you're like, okay, well, when does that happen? Thinking in terms of the unit circle, it happens, well, a couple of times. It happens at pi over 2 and 3 pi over 2, but the only value that it happens at in this domain would be pi over 2, so c would be equal to pi over 2. Now, there is a Desmos way you can handle this, because, you know, why wouldn't there be? And I'll try to do it carefully so I can make it something savable, but I'll probably do what I normally do as much as I can with you, and then I'll tweak it later on to make it look super nice, or at least as super nice as I'm capable of making something look. So anyway, you know you have some function f of x. So I'll put in a note here, input function. All right, so then I would say f of x, I like to put a function in as a placeholder. So I'll put in f of x. I'll keep it relatively simple. I'll go to the first example, x squared. All right, on the interval that they give us, which is a to b. So the way I would represent that in Desmos, squiggly bracket, a less than or equal to x less than or equal to b, which allows me to create a couple of sliders to establish my domain. All right, so 1 to 5, for example, in this case. So it's only going to give me the part of graph that I care about, which is nice. right? There's something that I've been meaning to try. I keep forgetting to try. I don't think it's going to work, but I kind of want to just give it a shot. Nah, it was a thought. It would have been nice if I, create a slider and then I could make the zoom take on the value of the slider. I'm sure there's a way to do it coding wise, but I just don't know how to do it yet. Right. So I want to actually have some nice coordinates. So I'll make a little table here so I can connect the dots, A, F of A. And this is very similar to slope of the secant. I believe I have that applet up there. B, F of B. Oh, there we are. All right, so we have some points, but I want them connected with a line segment. So let me just slide up and let's see if it'll work. Turn on that line, make it a different color, make it, I don't need to change the opacity. And I'm going to do, I'm just going to throw a couple lines in here so I can sort of scroll it up. I want to make this like 5, I guess. Yeah, a little bit, just a little bit thicker so it stands out, something like that. So that's my average rate of change, my slope of the secant, or that's my secant line. I want the slope. All right, and that's going to be F of B. Let me put the fraction in first. Minus F of A over B minus A. So that gets me the 6 that we came up with when we did the problem together. Got all these extra lines here that I don't need. All right, so I have my slope of the secant line. Now I just need the slope of the tangent line. The thing is, the tangent line slope is sort of unknown to us. I mean, as it turns out, in this case, it's linear, so it's going to be based off the same functions, easy to solve as we saw. But I can type in F prime of C and add a slider for C, and that'll give me the instantaneous slope at some value C. So let me make a little note for that. And like I said, I'll clean this up later. But now that I know my average rate of change depending on A and B, I can now slide my slider to identify the instantaneous slope that corresponds with that. And once I settle on that C value, then I know that I have my result. All right. Now it is reliant on the ability that you'll get a somewhat clean answer, cleanish answer. But even for trig problems, it should work, except you're dealing with multiples of pi. So you might have to change your increments on your sliders, but that shouldn't be too bad. All right, so this is mean value theorem, MVT. So let me go back and do that with sine of x and see how it goes. The sine of x. It's funny. I mean, sidebar. I'm teaching in every one of my other classes all the concepts that one would need to be successful in this class. Like in algebra, in my algebra class, I'm teaching function notation. in my pre-calc class right now, I'm teaching graphing trig functions and analyzing with unit circles. You know, like you put all the material together, it would be like a perfect precursor for this class. It's just, you know, it's just unfortunately not the way education works. Why doesn't it work that way, you ask? I have no idea. I mean, the answer to everything else is money, so I'm guessing that. Right, so 0 is my A value. I can't slide a slider to get to pi, so I'll just type that in. The thing is, when you put an irrational number in for a slider value, you lose the slider ability until you change it out of being an irrational number. Right, so I have it in as pi. If I want to get the slider functionality back, just put in some dummy value that's not irrational, and you'll get the slider function back. All right. So now I have something that looks very mean value theorem-ish. So that's good. Now what I would need to do, because I have my slope of the secant line, I would need to slide my slider until I got that 0. The problem is, I mean, if you're able to pull a pi over 2 out of this, I mean, good for you. But what I would say is, all right, well, we know we're dealing with a trig function on a particular domain. So why not put that domain? Oh, you know what? That's something. That's something I may be able to do. Yeah, you could put the domain as the bounds for C. That's kind of cool. I just figured that out. I should have known that one. Right. But this will start whatever you put in as A and B. So 0 and pi, those will be the bounds for C. That's pretty cool. All right. So now I can kind of slide over and get maybe a better estimate. You know, I want to get around 0 as close as I can to it. I mean, it's a pretty safe bet. Like if you know your decimal variations of pi, you can look at this and say, well, it's probably pi over 2. If A is 0 and B is pi, this is halfway through the scale. But another way you can handle it would be to change your step. All right. So a good step for trig values is either pi over 6 or pi over 12. And that's because pi over 12 is a common denominator for 3, 4, and 6. All right. So if you do that, then you'll get the more recognizable values. And then it's just a matter of doing a conversion. So you see, I get the clean f prime of C equals 0. So I see my slope of the secant and my instantaneous are the same. That's happening at this decimal value. I would just have to figure out what multiple of pi that is, which is actually easier than it might seem. All I would do, I got to type it in because I'm using a touchscreen. But if you have a mouse, copy and paste that. As many digits as you can get. I think that's a 9 at the end, but you know, I think that's all I can really see. We know that this is some multiple of pi. So divide out a pi and it'll tell you what pi needs to be multiplied by to give you that decimal. So this is saying pi times 1/2 or pi over 2. All right. And so that confirms that that's the appropriate decimal, and now you have the value. All right, all by using this applet. All right. So like I said, I'll clean this up and get it saved on Blackboard. You've seen throughout the semester that there's more and more stuff stored up on Blackboard in terms of calculators. Those are all there for you. So take them, use them, save them, modify them. I mean, the hope is that you're never working from scratch. You can always build off of something. And if you take one of mine and you make some serious improvements to it, send it back to me and let me know. Because I like to benefit from this stuff too. You know, it'd be pretty cool. All right. Now, Rolle's theorem will only apply if we're dealing with continuous differentiable functions on the closed interval. Right. So polynomial functions, sine and cosine functions, those are continuous differentiable. Those are smooth curves. They don't have any asymptotes, holes, jumps, anything like that. Right. They're definitely not piecewise. Right. When you get to reciprocal functions like cosecant, secant, cotangent, those have asymptotes, so does tangent. different story, but it really just matters if on the closed interval, it's continuous and differentiable. So even if you have something like a tangent function, if the part of it that's discontinuous, like pi over 2, is not part of the domain that's given, then it's irrelevant, and you can still consider it continuous and differentiable on a closed interval. Right? So what we would say is that this is continuous and differentiable on the interval of 0 to 3. All right, that is the closed interval. That's the relevant closed interval. So we can state that. That's one condition that needs to be met. Right? You don't have to prove it to me. You just have to make the statement. All right? Proving it was like 2 units ago, so we're good there. All right? So that's verified. The other thing is that f of b has to be equal to f of a. All right, so again, here's A, here's B. So f of 3, or f of A, f of B, doesn't matter what order you do it. Equality is commutative. All right, so we would do a quick substitution, or if you want to roll the dice, you could just believe that it's true. All right, I don't know why I put an A there and then a 0. All right, but if I plug the 0, plugging in that is easy enough. Plugging in the 3, I get -9 plus 9, which is equal to 0. That's also true. So this condition is also met. All right. So if these two conditions are met, then we can take the derivative set it equal to 0. And in doing so, we will have determined that this part is Rolle's theorem, the act of being able to set it equal to 0. And in fact, this kind of should have been right around when we were making sign charts. That's when this lesson should have happened. All right. Because this is the justification for why we would take the derivative and set it equal to 0 and solve. And so if you felt like there was something missing at that point, like why 0? Why were you allowed to do that? This lesson should actually explain that. All right, so that was totally my bad. So continuous and differentiable. First off, the continuous part would be if there are no vertical asymptotes, no holes, right? No jumps, right? Or any other types of discontinuities like oscillating discontinuity, and polynomial functions have none of those. So that checks all the boxes. Differentiable would be a continuous function, which we now know this is, that also doesn't come to a sharp corner anywhere or a cusp, right? Never comes to a point, right? Same deal. Parabolas never come to an actual point, a sharp point. So it's not going to be an instance where we're dealing with something that's non-differentiable. Yeah. So the question is, so we can just graph it and check it. Yeah, like a couple of units ago, I'd make you prove it, but now it's like that would be like double jeopardy. I don't need you to prove it anymore. Just take a look at the picture. Right? So, and in fact, you could even use the mean value theorem applet to give it a quick look because that already has the domain stored into it. All right. So then, again, Rolle's theorem is just telling us that there's a location on the interval where the derivative is equal to 0. All right. So again, this is sort of like what they were saying, or what I was saying before. Technically, this should be, some point C on this interval. I made my arrow a little too long, a little obnoxiously long. There's some point C on this interval. Where the first derivative is equal to 0. So we would say f prime of C, which would be -2C plus 3 is equal to 0. either way, you can leave it in terms of X and solve, or you can plug in the C and solve it. It's going to give you the same value. All right. So one is, again, the by the book textbook approach. The other is more of the freewheeling and, everybody does it this way approach, So add the 2x to both sides. Divide, you get x equals 3/2. Or you can write it as c equals 3/2. But since x equals c, we would say c equals 3/2 anyway. All right, because there is some point where x is equal to that constant value of c. All right. So what I was mentioning before with the second example is that there are instances where Rolle's theorem and the mean value theorem coincide. So this applet that we created for the mean value theorem can also be used for Rolle's theorem, because what's happening is if the heights are the same at the endpoints, then the average rate of change between those two endpoints would have to be equal to 0. If the average rate of change is equal to 0 and the mean value theorem tells us that there would be some instance along the closed interval of a to b where the derivative is equal to the average rate of change, then there would be some instance where the derivative is equal to 0, which is what Rolle's theorem is saying. So I could actually use my mean value theorem applet, I'm calling it an applet for lack of a better term, to apply a Rolle's theorem solution, or to determine a Rolle's theorem solution. So if I say negative x squared plus 3x on the interval of a to b where a is 0 and b is equal to 3, I got my graph. You can see that the average rate of change is equal to 0. It's horizontal. Slope of the secant line, average rate of change. I'll probably throw that in later, aka average rate of change. Right. Instantaneous rate of change, I'd have to identify the location in which that would be equal to 0. So let me just change my settings back, because I don't need this to be in terms of pi anymore. I'd want this to be integer values, but even going by ones wouldn't necessarily make sense. So what I would do is just leave this empty so that I let Desmos decide and allow for it to have its own tolerance. And it's going to go to the nearest 100th. So I'd keep scrolling, and you could see my instantaneous slope is decreasing as I increase my C value until I get, getting closer and closer. I'm pretending that I don't see the final answer right in front of me. At 1.5, we have an instantaneous slope equal to 0, which is what we came up with when we solved the Rolle's theorem problem, right? So the remaining problems here are kind of along those lines, but you can see that there's a pretty spicy one when it comes to that trig function at the bottom, the cosine and the tangent problem. So I'm going to put stars on the remaining questions here, and we're going to move on to something called L'Hopital's rule. Right, it's the other topic that I forgot to teach in the last unit. All right, so we'll review these again next class, the ones I put the stars on. But now we're going to talk about L'Hopital's rule, which is really kind of, honestly, I have no excuse for forgetting to teach this one, because I even teased this one earlier in the semester when I was giving you those trig rules involving sine and cosine, and I said, for now, you'll have to take these rules on faith. There were limit rules involving trig functions. And it was like, well, for now, just believe me that it's true. Later on, I'll prove it to you, and it'll be great. It'll blow your mind. And then I forgot to blow your mind. Now I'll do it now. Right. But and this, I forget where I got this table from. Honestly, it might have been straight out of Wikipedia, but I just didn't want to type it. I mean, you see all the stuff here. The idea, and they give you transformations and stuff like that. We don't really need that, But what we need to be able to do is recognize certain indeterminate forms. All right, these are values that you would think that you would know the answer to numerically, but there's no possible way to determine the value of these numbers, right? What L'Hopital's rule actually does is it allows us to determine limits for indeterminate forms, right? The only indeterminate form that we worked with directly so far, well, actually the only ones that we worked with directly were the first three. Just instances that involve ratios involving zeros and infinities, right? 0 divided by 0, you know, whenever you see 0 in the bottom of a fraction, we tend to think undefined, except that one instance where you have 0 also on the top of the fraction. That's what makes it indeterminate, right? Because it's philosophical, but it's also, you know, a technical thing. And say, if I take 0 things and I want to divide them up among everybody, how much is everybody, how much of the nothing is everybody going to get? They're each going to get nothing, right? But if I have 10 items and I want to divide that up amongst nobody, how does that work? You might say, well, you just keep all the 10 items to yourself. And you say, well, wait a minute, that's dividing it among the one person, right? Because if you're one person keeping all the items, somebody's getting the 10 items. That's 10 divided by 1. How do you divide it amongst nobody, right? Where do those 10 items go if nobody's getting, right? If you have nothing to start with, it really doesn't matter if there's 10 people you're dividing it among or 50 people. But if you're trying to divide it amongst nobody, what do you do with the quantity that you have? Even if that quantity is nothing, it's like conceptually, that's when things start kind of falling apart, right? So then the same idea holds true for infinity over infinity, just on the other end. But also you can sort of think about it, and this one's a little easier when you think, all right, if infinity is some moving number and I want to divide it by another infinity, is that other infinity at the same place as the first infinity? If infinity is a moving number, if it's always on the move, how do I know these infinities are keeping pace with one another? Since we can't perceive infinity, I can't really pin that down. So indeterminate, we really kind of look at it as the I can't determine it form. All right. So I'm looking at this being like, well, I don't know what form of infinity we're at. You know, are we at, I mean, because when you think about it, depending on how you count, you might get to one infinity might be outpacing another infinity. Right? You might have a slower movement towards infinity. Right? And a very simple case of that, I mean, it's kind of weird to think about it, but I'm just going to turn this off so I don't actually delete it all. But if I have y equals x, and I have y equals 1/10 x, they're both going to infinity. All right, the blue line and the green line are both going to infinity because one of them is going there faster than the other. So as I move along this x value, let's say x equals 0, I start sliding along. That blue line is outpacing the green line, and it appears like it always will. So since infinity is, like I said, a moving target, it's always on the move. It's not like we could ever just get there. Oh, I'm sliding the wrong slider. Let me move this up to like 300. It's not like I can ever get there, but I can establish a relationship if I know what the two functions are. And this relationship is for these x values as I'm getting closer and closer to infinity. The y values are also approaching infinity, but one of them is going to be a stronger infinity than the other at any moment of x. So since we don't distinguish between the infinities numerically, we don't call one like big infinity and one like slightly littler infinity. If we say infinity over infinity, we don't know what the relationship is between those infinities. So we can't just say that the answer is 1, like any number divided by itself is equal to 1. I mean, that would be nice, but that's not something we can assume, right? And again, same idea, anything involving the infinity, we would most likely say that that's an indeterminate form, because how do I take nothing and divide it up among a group of people that are ever expanding, right? Take a 2. Take 2 and divide it among 2 people. Easy enough. Each person gets 1. Take 2 and divide it among 4 people. Each person gets a half, right? If I tell you take 2 and divide it among 2 people, and then I start dividing it out, I give the first person 1 because I figured I did the math, 2 people, and I have 2 items. First person gets 1, and then I've already given it to them. There's no give backsies or whatever. Then you say, oh, wait a minute, there's a third person. I'm like, oh, now what? Right? That's what's happening here. Infinity is always on the move. It means that at any moment, the group is always expanding in size. So how can I take a number and divide it by infinity if that denominator is always on the move? So indeterminate, right? Infinity minus infinity, same idea as infinity divided by infinity. I wouldn't say 0 for the same reason I wouldn't say 1 when I said infinity divided by infinity, because I don't know that they're the same infinity, right? And really anything, like I said, involving infinity, because it's on the move, it's something that we can't conceptualize. We can't actually get there. We don't know what it's like. Well, if infinity ever called it quits and said, I'm going to stop right here, and we could catch up to it, that'd be one thing. But we can't. So I don't know what 1 to the infinity is going to look like. I mean, I would imagine it would be 1, but I can't make that assumption, right? 0 to the 0th. When we say anything to the 0th power is equal to 1, that's a strange thing to begin with. So when we say 0 to the 0th power, that even makes things stranger, right? And there's more, and I'll explain that one in more detail later on, because that's when we have a variable raised to a variable power. Different weird things happen with that. So we're going to table that one for a little bit. And the same thing with infinity to the 0th power. All right. And we'll see some examples that relate to those, and you'll say, oh, okay, now I see why that one doesn't really make much sense when we're thinking about it just off the top of our heads. But what L'Hopital's rule is telling us, and you can see the notation here, it looks kind of funky, but if you really dive into it, we say that and just kind of break it down to a simple process, if you have a limit that produces a result that's an indeterminate form, what you can do is find the derivative of the numerator of that function or that relation or rational expression, whatever, and divide it by the derivative of the denominator of that expression, and then reapply the limit. Right? It's strange because when you see a quotient, you tend to think quotient rule. This is actually going to violate the quotient rule, right? And I'll show you a little bit more of that in a second. Right? But this rule, L'Hopital's rule, it does that. So we'll take a look at the first example. Actually, we'll do the first 3 examples, and then that'll be it for tonight. But so if I plug in a 3, just going back to unit 1, plug in a 3 for x And we get 3 plus 1 under the radical minus 2 over 3 minus 3. All right, so you get square root of 4, which is 2, minus 2, which is 0, over 0. All right, so that's indeterminate. All right, that's my invitation to use L'Hopital's rule. All right, so invitation to use L'Hopital's rule, which I abbreviate L''HR. L''H for L'Hopital and R for the. All right. So what do? We take the derivative of the top, which is going to be, well, and if I rewrite this, it's x plus 1 to the 1/2 minus 2. I'm going to take the derivative of just the top first anyway. 1/2 x plus 1 to the negative 1/2. The 2 is irrelevant because it's constant. Derivative goes to 0. Then I'm going to take the derivative of the bottom separately, as if it's its own problem. All right, the derivative of x minus 3 is just going to be 1. This is all with respect to x. So in fact, I mean, I'm going to write an extra step in here. You wouldn't have to write this. I just want to do it so I can be absolutely clear what we're doing. We're taking the derivative with respect to x of x plus 1 to the 1/2 minus 2. And then we're taking the derivative with respect to x of x minus 3. All right. That gives us this simplified expression, which we could actually go a little further with, but we don't want to go crazy with the algebra until we find out it's necessary to go crazy with the algebra. So then what we do is we apply the limit to this new expression. So limit as as x approaches 3 comes along for the ride. And now I'd find the limit of this new expression, which would be 1/2 3 plus 1 to the negative 1/2, 1/2 4 to the negative 1/2. So that would be the reciprocal of the square root of 4. So this results in a 1/4. Right, and so that would be my result. Right, that's my limit. Now we could verify. Again, just like before, I'm going to try to work around the other applet. But if I put the original function in, I'll put it as y equals the square root of x plus 1 minus 2 and an x plus 3, oh, I'm sorry, x minus 3. Go back to the home zoom. They're saying find the limit as x approaches 3. At 3, it's undefined. But if I get closer and closer and closer, close as I can, you see, it's hard to see on the left side of the screen there, but that does look like it's hitting around 0.25. If I zoom and enhance, it appears that I'm getting closer and closer to 0.25 for the y value. All right. In fact, it even fools Desmos into thinking it is 0.25 because it's rounding to 2 decimal places. It's definitely 0.25000 blah 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 something, but it's rounding it to 0.25. But you can see that that's what it's trying to say. So the answer is 0.25, but this will flesh that out for us. And this actually has a lot of basis in what we were doing involving Newton's method. Okay? This is sort of an expansion on that. It has to do with the ratio of the slopes of the two functions. It turns out that the limit of the ratio, if for only for indeterminate forms for some reason, I haven't really figured that part out yet, but for indeterminate forms, the ratio of the slopes the instantaneous slopes of the two functions is the same as the limit for the ratio of the two functions themselves. Just fascinating. Right. Now, if we apply one of the techniques from the first unit to find the limit for number two, whether it's the horizontal asymptote technique or the end behavior model technique, either way, we could come up with the 5/3. However, if we just did direct substitution would give us 5 times infinity squared minus 3 times infinity plus 1 over 3 times infinity squared minus 5. Now, bottom line is, this is going to be some kind of infinity over some kind of other infinity, all right? Not necessarily equivalent infinities, all right? And that's kind of a mind-bending sort of thing, right? The idea that we could have multiple infinities, even in the same problem, and they don't necessarily mean the same thing, right? But it's all relative, right? So this is an indeterminate form, right? Assuming that we're not using any of the shortcuts that we did in the first unit. But it's also, like I said, an invitation to use L'Hopital's rule. Which honestly, I mean, I was sort of naive and foolish back when I was a calc student. And I would say, man, I wish I knew this rule back when we were talking about limits. But I didn't think about the fact that I didn't know how to take a derivative when we were talking about limits. So this wouldn't have been very useful for me. Right? But yeah, it's kind of nice to know in retrospect that that there are other ways to do these things now. So we would be finding the derivative of the numerator. And again, I'll show that intermediate step, even though it's not necessary for you to write. I'm going to find the derivative of 5x squared minus 3x plus 1. We're going to divide that by the derivative with respect to x of 3x squared minus 5. And then we're going to apply the limit to that. All right. So then finding the derivative here would be 10x minus 3 over 6x. Oh, just 6x. All right. But then we run into an issue here. Not really an issue. More so, it's just the next layer to the problem. If I apply the limit, I get 10 times infinity minus 3 over 6 times infinity. So that again seems like two distinct flavors of infinity, perhaps. If I could ever meet infinity, I can get a clear answer on this. I hope he's nice though. Or she, or they, or I don't know what right stuff is anymore. Okay. So the indeterminate invitation to use L'Hopital's rule. So now I can apply it again. So d dx, 10x minus 3. The derivative with respect to x is 6x. So we got a second layer of this L'Hopital's rule going on. All right. So derivative of 10x minus 3 is just 10. The derivative of 6x is just 6. So I'm looking at the limit as x approaches infinity of a constant. That's not indeterminate. The limit of a constant, I think it said derivative. The limit of a constant is equal to the constant itself, which would be 5/3. All right, so we don't want to toss aside our shortcut rules completely. because sometimes they're not necessary, but they're shortcuts for a reason. They streamline the process substantially, because by looking at the original expression, we could say, well, the exponents are the same, so I'll take the ratio of the coefficients as 5/3 because that's what the horizontal asymptote is. However, this is a nice analytic justification for why that works the way it does. Exactly. The second level to the dream. Now, we will get to some cases where it'll feel like we're in limbo. That's on the next page. Right, but this one, I think, is like kind of the moment we've all been waiting for, maybe. This is the rule from back in the first unit when we were talking about limits, where I said, well, this is a rule that you just have to believe is true, right? The limit, and it was as a approaches 0 of sine a over a is equal to 1. So this will be equal to 1. However, if I plug in a 0, I get sine of 0 over 0, which is 0 over 0, which is an indeterminate form. Now, we were only able to verify this one graphically, that it was true, that it would be equal to 1, but now we're going to be able to verify it analytically. So we do that by finding the derivative of the top and the derivative of the bottom. And apply the limit as x approaches 0 to that new ratio. All right. The derivative of sine of x is cosine of x. The derivative of x is 1. So now I'm just finding the limit as x approaches 0 of that. And if it gives me something indeterminate again, I'll have to continue the process. But if it doesn't, so cosine of 0 over 1, if it doesn't, I'll have my answer. Cosine of 0 is 1, divided by 1 is equal to 1. And that's the analytic justification for a rule that we were taking for granted. And I asked you to believe me was legit and true and all that good stuff. But now you see that there is a basis for being able to make that claim, aside from, hey, that's just the way the graph looks.